Section 15.7 in Thomas's textbook. It's called Triple Integrals in Cylindrical and Coordinate System, whereas in Stewart's textbook, um, this topic comes into two separate sections, 15.7, 15.8. But in both textbooks, I'm going to talk about part one. In other words, I'm going to divide this section into two separate videos. First, I'm going to introduce what cylindrical and spherical coordinates is in the next video, so we can talk about triple integrals in cylindrical and spherical coordinates. If you remember, in Cartesian coordinate system in 3D, or sometimes it's called rectangular coordinate system, in order to go from 0 to a random point in space, you had to go x many units along the y-axis, y many units along the x-axis, y many units along the y-axis, z many units along the what? Along the z-axis to get from origin to the point. In cylindrical coordinates, the point is on a cylinder. That's why it's called cylindrical coordinates. As a matter of fact, cylindrical coordinates is three-dimensional version of polar coordinates. So it's the polar coordinates in 3D. Remember, polar coordinates was what? Was on the floor, which the point, let's say P prime, was what? R comma theta. Now, the minute you add a height to it, the dimension height, so now you are in cylindrical coordinates. So the point is what? On a cylinder, circular cylinder. So the way you do this, from the x-axis, you go theta many units, just like polar coordinates, counterclockwise, and r units what? From here to a point on the what? XY plane. And then you go all the way up z many units till you hit the cylinder. And the point is r theta z. That's the order of the components of what? X, Y, Z. Now it becomes r theta z in cylindrical coordinates. There are some restrictions, just like polar coordinates. R is positive because it's a measure of distance. All right. Theta can go from 0 to 2 pi. Turns out these are not the only two ways you can go from 0, 0, 0 to a point in space. You can also get to the same point, x, y, z, via spherical coordinates. As you can tell by the title, the point will be on a sphere. In this case, what you do, you go theta radians, from the positive x-axis counterclockwise, correct? And then you go phi, so this Greek letter is called phi, many radians from the z-axis, or think of it from the North Pole, but clockwise downwards. Then you draw this line right here, which is known as a rho. You get to the point P. So in other words, you go theta radians from the x-axis, phi many radians from the z-axis. This guy goes counterclockwise, this guy goes clockwise. Then you draw this line here from point origin to point P, which happens to be on the sphere. That will take you to the exact same point as you had x, y, z. I wish I could demo this live so you can see it really gets you to the same point. However, I'm making the video, it's kind of like hard to explain phi and theta. But basically, remember, this is exactly the concept of GPS. Theta we used to call longitude and phi is the latitude. So what's happening is we have, just like, any other coordinate system, like, cylindrical, we have restriction. Rho, that's what this Greek letter is pronounced, rho. is distance, so it has to be positive between what? Origin and the point in spherical coordinates. Phi can only go from North Pole to South Pole. In other words, phi has a restriction. Remember how phi gets to be constructed. You always go from North Pole to South Pole. So here phi is 0, here phi is pi. You're only allowed to go that far down. So therefore phi can only go from 0 to pi, and at North Pole phi is 0, at South Pole phi is pi, and you always go clockwise. Okay, so if you stop at pi over 2, so you are on the xy plane. Do you see it? But theta is free to go 360, 0 to 2 pi. But phi cannot exceed pi. Now, going back to the cylindrical coordinate system, you remember the conversion formulas. X equals r cosine theta, r is equal to sine theta, r squared is equal to y squared plus x squared, and tan of theta is y over x, correct? You remember this magic triangle right here, and that's basically I'm getting my relationships from. However, in spherical coordinates, if you kind of extend this over here, take this line from here and draw it here. This is a 90 degrees triangle, namely OPQ. So if I draw the OPQ here, this guy is the same as R, this guy is the same as Z, and this length is the same as what? It is rho. So if you kind of transfer that triangle over here so you can have a better view. So this is how that triangle OPQ looks like. So from this triangle, I can tell sine of theta is opposite over adjacent. So that means R is equal to rho sine phi. And what? Cosine of phi is adjacent over what? Hypotenuse. So Z is equal to rho cosine phi. However, from cylindrical coordinates, x was equal to r cosine theta, y was r sine theta. So if you go back and what? Replace this guy, r, with rho sine phi, and then this r with also rho sine phi. So the conversion formula from cylindrical to Cartesian becomes x equals rho sine phi cosine theta, y is rho sine phi sine theta, and z is still rho cosine phi. So these are the conversion formulas from spherical to Cartesian. But please don't forget the restriction on these three parameters. Rho is always positive. Phi goes from 0 to pi, so that goes from North Pole to South Pole clockwise. But theta can go 360. Correct? If phi stops at pi over 2, 90 degrees, you're on the floor. So what we have now is what? A couple of examples of conversion. Let's say you have the components of a point in Cartesian. They want you to express these components in cylindrical and spherical. In cylindrical, you need what? You have the z, so there is no need to convert this. You just have to convert x and y into what? R cosine theta and R sine theta, correct? So, excuse me, what we need is express what? Sorry about that. Replace the x with r, y with theta, and z stays, because this is how the components of the same point in Cartesian looks like in what? Cylindrical. So I should no longer have x and y as my component of the points, but it's okay to keep the z. So z stays, but x gets to be replaced with r and y gets to be replaced with theta. Remember, r was equal to what? Square root of x squared plus y squared. So here's my x, here's my y. So I, use this relationship, and lo and behold, r is equal to 5 square root of 2 over 2. Theta, if you remember, tan of theta was y over x, so that implies theta is tan inverse of what? Y over x. So when you do this, you will end up with pi over 6, which is 30 degrees. Therefore, this point in Cartesian is equivalent to what? 5 square root of 2 over 2 comma pi over 6 comma 5 square root of 2 over 2, which is r theta 0 in what? In cylindrical coordinates. Do you see it? Cylindrical coordinate system. So these 2 points, they overlap in three-dimensional space because it's just getting to the same point via different routes. In spherical, remember we had r is equal to rho sine phi. So what does that mean? I know r from here. Remember, r was 5 square root of 2 over 2. Okay. And I know rho 2. How? If you remember from, let's say, over, let's see now here, rho squared, which is hypotenuse squared, is equal to r squared plus z squared, correct? But r squared from what? Cylindrical coordinates is x squared plus y squared. So rho squared is x squared plus y squared plus z squared. There goes the relationship between rho and x and y and z. So rho squared is always x squared plus y squared plus z squared. So therefore, what does that mean? That means rho is equal to square root of what? X squared plus y squared plus z squared. So that's what I did here, and I came up with rho is equal to 5. Okay, so I got the rho, I got the r from here. So now I can what? Solve this equation for phi, because if sine of phi is what? This guy divided by 5, so phi is what? Is going to be what? Sine inverse, is that right? Sine inverse of that guy, which is the square root of 2 over 2. But that's exactly the same as pi over 4. Is that right? So now in some books, the order of what? Components of the point goes rho phi theta. In some other books, they go rho theta phi. Either way is fine. So here's rho, which is 5. Phi, I just found that is pi over 4. Theta, I knew it from part A, which is pi over 6. In other words, this is exactly the same as what? 5 square root of 6 over 4, comma 5 square root of 2 over 4, comma 5 square root of 2 over 2. In other words, over 2. In other words, this point in Cartesian is equivalent to this point in cylindrical, and that's equivalent to this point in what? Spherical. All of these 3 points will get you to the same common point in space. So that's the beauty of conversion. The question is, why am I converting to begin with? Well, why did we convert from double integral from Cartesian to polar? Didn't it make the integral easier? So sometimes it's easier to what? Kind of perform the triple integrals, like in the case of polar coordinates, a double integral to polar. And in triple integrals, it will be easier to go from Cartesian to either what? Cylindrical or spherical. It just makes the computation a lot easier. Okay, how about the graphs? In cylindrical coordinates, if they ask you graph r is equal to constant, like let's say r is equal to 3, the graph is not a circle, it's a cylinder, which what? Opens up or stretches along the z-axis. And the radius is 3, and the center is what? At 0, 0, 0. That's the graph of r is equal to constant in cylindrical coordinate system. If theta is constant, like let's say they ask you graph theta is equal to pi over 4 in cylindrical coordinates, that's a half plane attached to the z-axis, making an angle of theta 0 with the positive x-axis. So for theta, graph of theta equals pi over 4 from the x-axis, go counterclockwise, what, pi over 4, and graph this so-called half plane, which is attached to the z-axis. So the graph of r is equal to 3 in cylindrical is a cylinder. Graph of theta is equal to constant in cylindrical coordinates is half plane. The graph of z is equal to constant. We know from chapter 12, it's just a plane parallel to the xy plane, 5 units away from the floor. So we know that. In spherical coordinates, if rho is constant, okay, the graph is sphere of radius rho 0, and the center is always at 0, 0, 0. For instance, if you ask me to graph rho is equal to 2 in spherical coordinate system, the graph of rho is equal to constant is a sphere. So in this case is a sphere. A radius is equal to 2, which we show it with Greek letter rho. Okay, but the center is at 0, 0, 0, correct? What if phi is equal to constant? If phi is equal to constant, it all depends on the value of the phi. For instance, if phi is between 0 and pi over 2, you get the upper half of a cone. So what you do from the North Pole, you go pi over 3 units. Let's say you are asked to graph phi is equal to pi over 3. So you go from North Pole, pi over 3 units, what, clockwise, graph these, and then lo and behold, that would generate a cone because theta can go from 0 to 2 pi, and rho can be anything as long as it's a positive number. That generates a cone. But in this case, because phi is acute angle, so it's the upper half. If phi is obtuse, that means it's between pi over 2 and, excuse me, pi, right? Let's remember the restriction of the phi is up to and including pi. That would be obtuse. So now you would get the lower half of the cone real, right? You see that? Because you go from North Pole towards the South Pole, what? Clockwise, so you'll be right here. And because theta is missing, so theta is from 0 to 2 pi, and rho is any real number greater than 0. However, if phi is pi over 2, then you are on the xy plane. If theta is equal to constant, well, that's the same case as what? Cylindrical coordinates, which is half plane attached along the z-axis and making an angle of theta 0 with positive x-axis. So it's the same idea here. So rho constant, sphere. Phi constant, cone. Depending whether it's acute or obtuse, you either get the upper half or the lower half. Theta constant, half plane. So please keep these graphs, important graphs in mind. Sometimes they have to, or we have to convert equations, not points, but equations into cylindrical or spherical coordinates. I could go from cylindrical to spherical, spherical to cylindrical, cylindrical to Cartesian, and back and forth. In this case, the equation is given in Cartesian. They want me to express the same equation in cylindrical and spherical coordinate system. In cylindrical, you and I, we both know x squared plus y squared is r squared. And this is how the equation should look like in cylindrical coordinates. Z should be a function of x, r, and theta in what? Explicit form. Do I have to express the equation in explicit form? Not really. Just like you didn't have to what? Express the equation in explicit form for Cartesian form. Sometimes you have to leave it in what? Implicit form. But if you decide to what? Express the final answer in explicit form, z has to go first and r and theta has to go to the other side of the equation. So in this case, what we have is r squared plus z squared is equal to 2z, that's a z, correct? So now if I move the r square here and 2z on the other side and complete the square by adding 1 to both sides of the equation, so the left side becomes a perfect square. When you solve for z, this is what you get. In what? Cylindrical coordinates, which happens to be in explicit form. Do you see it? In spherical coordinates, this is how the function should look like in explicit form. So this is like explicit form. Is that right? So instead of z is equal to function of xy or z is equal to function of r theta, rho should be expressed as a function of theta and phi. You and I, we both know x squared plus y squared plus z squared is rho squared. You remember that, don't you, from here? You remember where to go? From here. Rho squared, we decided is r squared plus z squared from this right triangle. But r squared is x squared plus y squared, so rho squared is x squared plus y squared plus z squared. So I'm going to replace that with rho squared. Then I'm going to replace the z with rho cosine phi. If you remember, that also comes from right here. One of the conversion formulas, z is equal to rho cosine phi, not theta, but phi. Okay. Then what I do, I move this over and factor out the rho. I get either rho is equal to 0 or rho is equal to 2 cosine theta, phi. But I choose rho is equal to 2 cosine phi as opposed to what? Selecting both of these guys for an answer. Why is it that I rejected this? I only kept this because rho is equal to 0 is in this equation, is built into this equation. So there is no need to mention this twice, so it will be redundant. Why? If phi is equal to pi over 2, rho will be 0. So it's in here, because remember, phi goes from what? 0 to pi. When phi is pi over 2, you get rho is equal to 0. So there is no need to mention this. This should be the equation, what? The equivalent equation in spherical coordinates for this equation in Cartesian. And this is how the same equation pops in what? In cylindrical coordinates. Thank you.